So this video will contain examples of the following theorem. Let's suppose you have field extensions K, which is a field extension of E, which is a field extension of F, that are finite extensions. And what that means is you can think of K as a finite dimensional vector space over E, and E a finite dimensional vector space over F. And also, I guess, K is a finite dimensional vector space over F. The dimensions of those vector spaces satisfy this property. Remember the notation. This stands for the dimension of K as a vector space over the field F. Okay, so let me do an example. Let's consider Q. That's my first field. Q is a subfield of Q adjoined root 2. And this is a subfield of Q adjoined square root of 2 plus square root of 3. So let's see why, and let's find out the dimensions of each vector space. Well, a basis for this vector space over Q is 1 and the square root of 2. That's because a minimal polynomial or actually I should say the minimal polynomial. Minimal polynomials are unique because we define them to be monic. So the minimal polynomial is x squared minus 2. There's a polynomial with rational coefficients, degree 2, that has root square root of 2. So this is really a vector space. The basis is 1 and square root of 2. Every element in this field is a linear combination of these two basis vectors. Now, a basis for Q square root of 2 plus square root of 3 over Q square root of 2 is this element and 1. So 1 and the square root of 2 plus the square root of 3, because the minimal polynomial check this out. The minimal polynomial is, I'm going to write it this way, x minus the square root of 2 squared minus 3. So you could check that this element in your field, is a root of this polynomial. It's not too hard to verify. It's constructed this way. And this polynomial is a degree 2 polynomial. That means your basis is just 2 elements, degree 2 extension. Okay. Furthermore, a basis for Q, where I adjoin this element over Q, is different because I'm not allowed to use the square root of 2 as a coefficient of my polynomial if I'm only allowing rational numbers. I was allowed to say that this was a polynomial in the field Q adjoined 2, however. Okay, so a basis for this is 1 square root of 2 plus square root of 3, square root of 2 plus square root of 3 squared, and lastly square root of 2 plus square root of 3 cubed, because the minimal polynomial is x to the fourth, so it's a degree 4 extension, x to the fourth minus 10x squared plus 1. So I figured this out before the video began. You could verify, but if you plug in this element into x, you get out 0, and this polynomial has rational coefficients. Furthermore, this is an irreducible polynomial. At least at the very least, you could see that it has no roots over q, because the rational root theorem says such a root would either have to be plus or minus 1, and neither one is valid when you plug in plus or minus 1 into the polynomial. So it has no roots, and then you could argue that it also has no factorization into 2 degree 2 polynomials over the integers. So I'm not going to do that verification. We did it when we discussed how to check polynomials are irreducible over the rationals or not. But regardless, this is irreducible. This is an irreducible polynomial, and it's the smallest polynomial that has this element as a root as well. Thus, what the theorem says is, if I look at the largest field over Q, there are 4 elements in a basis. These 4 elements. So this is 4. Q adjoined square root of 2 plus square root of 3 over the field Q adjoined root 2. That has dimension 2 because, where are we? Right here, this polynomial is degree 2. I have 2 elements in a basis. So that's 2. And lastly, Q square root of 2 over Q is also 2. The minimum polynomial is x squared minus 2, and a basis is 1 and square root of 2. There we go. We have now shown that 2 times 2 equals 4. All right, wonderful. I'll do another example in the next video.